So, we begin the evening's public lecture by Professor Samir Mathur from Ohio State University. As you know, black holes are one of the most fascinating objects of study in modern science. Professor Mathur Samir will discuss the famous black hole information paradox, which traces back to Hawking's discovery of an operation of black holes. So it is my pleasure to let you know about it. And it is our pleasure to have him here to give this lecture. Please join me to welcome him again.
Okay, thank you for the nice introduction. So since this is a public lecture, I will go over the ideas of black holes that we have been talking in the regular lectures, but starting from a more elementary and impressionistic viewpoint. So I will not even assume that we know what general relativity is. I'll draw everything in cartoon form. And for the most part, I will not be using equations, but it will give us a chance to get an overview of all the ideas that we are going to get in the entire paradigm for black holes. Okay, so let's begin. So this is Stephen Hawking, of course, and as you know, if you have studied the puzzles with black holes, what Stephen Hawking is famous for is in showing that these two basic ideas of fundamental physics are actually in contradiction with each other. Or so it seems. In the end, we would not like that to be the case, because otherwise we have a big problem with our theory of physics. So this is, of course, Einstein, who invented general relativity, and once you have general relativity, a natural consequence of that is that you will get black holes. And quantum theory was, of course, developed by many people. I just put one person up there. There's Heisenberg, and that was a theory which started from the microscopic side, where you have the theory of atoms and so on, and there quantum mechanics is very important. General relativity, on the other hand, deals with things like stars and galaxies and so on, and in fact the whole universe. So this started from the macro side. But of course, if these are both completely correct theories, they are going to meet in the middle, and you can imagine trying to do the quantum mechanics of a large object like a star. If you can do the quantum mechanics of an atom, you can also do the quantum mechanics of a star. And so in principle, these two theories have to meet, and if you have general relativity and quantum mechanics together, you should get a theory of quantum gravity. So people were searching for a theory of quantum gravity for many years, and it wasn't quite working. And then Hawking came and showed that in fact there is a very basic problem. According to his argument from 1975, you actually cannot make them fit together. So that's a very serious problem, and that's called the black hole information paradox. We're going to take a very rough overview through the ideas of general relativity and what black holes are, and then we'll try to get into what we think are the ideas that might get us away from this paradox. And as we'll see there, we'll end up challenging the fundamentals of both general relativity and quantum theory, the way things will behave. Ultimately, they will fit together, but what we'll actually have to surrender, we'll have to surrender something, and that something will be our classical intuition for how black holes behave. So normally black holes are big objects, so we thought that classical physics would be okay for them, but we'll find it's not the case. We'll find that quantum theory actually completely changes the structure of black holes, and that's the only way to get out of the paradox. Okay, so that's going to be the main lesson at the end. Okay, so let's begin with an overview of general relativity from the point of view of somebody who doesn't know general relativity. So we can go back all the way to Galileo, who's, as the story goes, he dropped two balls from the top of the Leaning Tower of Pisa. They had different masses, but then he found, hey, they reached the ground at the same time. So he could have tried to plot a graph of the height y of the ball as a function of the time, and if they actually fall together, in fact, you'll get the same line. So that's, of course, the beauty of gravity. If you had some other force like electromagnetism, that's not true. Different objects have different accelerations, but in gravity, everybody accelerates together, no matter what the mass, and they all follow the same trajectory. And as I just said, situation is very special because it holds only for gravity. So if you have something like electrostatics, you have a charged plate here, it's carrying positive charge. If you bring a charged particle with positive charge here, it shoots up. If you have a negatively charged particle, it shoots down. A neutral particle doesn't want to go anywhere. So if you plotted the y versus t graph for these particles, they'll actually be all different depending on the charge. So given that there is something special about general relativity, you might wonder if we can use that in some nice way to make a theory for general relativity which is better than Newton's laws, because Newton's laws, of course, whatever force you have, gravity or electrostatics, you just put F equals ma, they both work. But in fact, there is some special beauty to gravity, because while everybody has a different track in electrostatics, they all have the same track in gravity. So that's of course called the equivalence principle. Everybody actually tries to fall together under gravity. But in fact, one thing we are going to challenge at the end, the reason we are starting so slowly, is that once it comes to something falling through the horizon of a black hole, it's actually the equivalence principle which is actually going to give. It's not going to work anymore, and we have to understand why. Okay, so in the traditional approach of Newton, if you have a x versus t diagram for a particle, if you want the motion of a particle, as Newton told us, if there's no force on a particle, particles move in straight lines with constant velocity, so that will be the graph. And if you actually had some force, then you would not get a straight line, then you will get a curve. So if you have a force, the graph will be curved. If there's no force, the graph will be straight, and that's what Newton would have told us. Of course, what you can try to do now is look at a curved sheet of graph paper. And on a curved sheet of graph paper, you can see I've tried to draw a curved sheet of paper here. You can try to draw a straight line. And then you can wonder what's the meaning of a straight line if the paper itself is curved. And that sort of can be defined, because a straight line you can call the shortest distance between 2 points. And if you define it that way, then even on a curved surface like the Earth, there are these straight lines. They're not really straight, but they're the shortest distance between 2 points. And so you can call them straight lines. And so this was Einstein's idea. Suppose there's some gravity in some region, then you want to describe the graphs of particles moving in that region. What Newton would have done was take flat graph paper and drawn a curved trajectory on it, and the curve would come from the acceleration of those particles under gravity. But instead, what we could do is take a curved graph paper and just draw the straight lines on it with their straight in quotation marks, because of course these are shortest paths. They don't look very straight when drawn like this, but there is a shortest distance between two paths. And he said, well, that would be the correct way to deal with describing the motion of gravity. So again, this is a particle with no force and the space is flat. If there was a force, Newton would simply give you still flat graph paper and a curved trajectory, but Einstein would say take curved graph paper and draw the straight line on it, and that would be the answer. Well, in fact, if you take the curvature of the graph paper to be appropriate, you do manage to get the correct path of the particle under gravity. But the beauty of this is that if you do things that way, you have already included the equivalence principle in a nice and beautiful fashion. Because now that you take a curved graph paper in this fashion, if this particle trajectory, this is the shortest line between 2 points, well then I can take a small mass particle, it will go here. I can take a heavier mass particle, it will have to go on the same trajectory, because after all my rule is follow the shortest path. So if my rule is that all the effect of gravity is in the curvature of the graph paper, and after that there's no physics in the particle itself, you just follow the shortest path. In that case, everybody automatically follows the shortest path. So you can't do this for electromagnetism, because if you try to curve the paper in such a way that the shortest paths give you the motion of a proton in some system, well, that would not be the motion of an electron, because it will actually have a different acceleration. But if you know that everybody follows the same track, then the whole curvature of the track can be actually absorbed in the curvature of the paper and actually let the track be the straight line. Well, what's the advantage of doing this? Why not just stick to Newton's way? In fact, it turns out that the answer you get by doing it this way is a little different from the answer you get by doing it in Newton's way, and in fact this answer turns out to be correct. So in fact, if we had flat space, of course things move in straight lines, but suppose you had the sun sitting in the middle of our solar system, it curves the space-time, and then the Earth would actually move in circles. And so if you do it this way, with the curvature of space, then you find a little different answer from what you got with Newton's laws. With Newton's laws, you know that planets describe closed ellipses, and they keep repeating themselves on those paths. But if you do it with general relativity, then you find the paths are not exactly closed. The ellipse sort of keeps precessing. It goes like this, and then like this, and like this. It's a small amount, but in fact, that's what matches observations and not Newton's laws. There was a question. Yes?
Can we say, in some sense, Earth's orbit is a straight line?
Yes, you can say that. if straight lines in quotation marks, in the sense this is the optimal path which extremizes the path length. If you draw the path length in the full space-time, four-dimensional space-time, and you take the Earth's position at one place and another place, if you find the path length which optimizes the proper distance between them, that is the path. So that's the way you find the entire path of the Earth in general relativity. And if you do that, you find that the path is not a closed ellipse, but the ellipse sort of slightly precesses each time. And for Mercury, you find this a small precession. Every century, you go through this many arc seconds. And in fact, it's a beautiful observation from almost a century ago that in fact that is indeed true. The orbits are not closed ellipses. They do want to precess. Okay, so that's what we have learned about general relativity, just as a cartoon form of general relativity, that all the dynamics of gravity is in curving space-time. It's not in the motion of particles, and particles just follow just the straight line paths, and that's it to gravity. But once space-time becomes curved, it opens the direction to doing a lot of interesting things. So once space-time is curved, you can just start drawing pictures, and you can start writing science fiction books. This is a flat space-time, flat piece of graph paper. If you put the Earth, the sun in the middle there, it makes a curved piece of graph paper. So you just put there, it just bends the graph paper, and up to here it's correct. And then what you can say is, okay, if I bend it enough and enough, maybe at some point I can tear a hole in it. Okay, and that's the rough way of thinking about a black hole. You take the whole thing and you tear a hole in it, and if things fall into there, they sort of don't come back. Of course, I'm being very rough, because this is supposed to be just a colloquial presentation of what a black hole is. So we'll just imagine that at some point I can just tear a hole in this, from which if I fall down, I can't come back, and for the moment, that will be our picture of the black hole. Well, you can do even more interesting things. You can make a wormhole. You can have something very curved space here, you go through a tube, and you come out on the other side. And that gives, if the space-time could have even this kind of shape, then let's say from here to my home in the US is like 4,000 miles, but there could be a small hole, like if I fall into this wormhole here, there might be a very short distance here, and this side may actually open up in the US. So then I could just jump in here and be home immediately. So in fact, you could make a lot of interesting kinds of pictures, and also a lot of interesting science fiction. We could disappear here and appear in some faraway galaxy almost instantly. What else can you do? You can imagine if this is your space and you make a little dip in it, this kind of hole. At some point, you could do this and pinch off a little bubble here. So you could like take the space-time here and break it off, and now you have a different universe. It's called a baby universe, and suppose you fell in there, now you're disconnected, and you'll never meet your friends here again. Okay, so there'll be a different universe there, and you can never see them. So if space-time could be disconnected, then these guys will never see each other. And then you have philosophical questions about, should we describe physics here by a wave function? This is a different wave function. Do we have to write a combined wave function for everybody? But most interestingly, if two things are disconnected, how will they ever know how far they are from each other? Will they ever connect back? Now, normally physics is reversible. If you can disconnect something, then you should also be able to connect back. Well, okay, disconnecting looks possible, but connecting back, you should have some idea of when they are coming close to connect. But if this thing is just the complete space-time, there's not like sitting in some other embedding space-time, there's no notion of two different manifolds being close. So then how do you ever describe them reconnecting? So there are many deep philosophical problems about how to set up physics if all these pictures, which we can just draw very easily with curved space, were true. Okay, one other thing you can do is have extra dimensions. We see 3 space and 1 time dimension around us. That's, we call them x, y, z, and then t for time. But there could be an extra dimension. I've just called it w here. As long as the direction is a very small circle, I may not be able to see it. So here is a small creature, an ant here, who lives in this space, but there's an extra dimension w, and if the ant can actually crawl around and see it, but if I try to see it and I can't see things this small, to me it'll just look like one line. So maybe we see only x, y, z, and of course time t, but maybe there are other directions w which are hiding around, but we just don't see them. Okay, so a lot of interesting things can be done. How many of these are true? They're all suggested by the fact that once you start curving space, of course you can do all of them. We now know that some of these things may not happen. So baby universes, at least from string theory perspective, seem to not be possible. These also, in general relativity, as long as all energies are positive, you actually cannot make structures like this. Today we are going to argue that a black hole which actually seems to make a tear in space-time also cannot exist. Okay, so that's a classical picture of the black hole will just not be true. So this you can do, but this you can't. Okay, so we are actually talking about a fairly radical change to how we think about black holes, but in fact if we don't do that, I will argue that you cannot get away from Hawking's paradox and you will lose quantum theory. So at the moment it looks rather puzzling, right? We have everything is so classical. These are enormous objects like on the astrophysical scale, and something coming from the foundations of quantum mechanics is going to come and tell us that what can or can't happen over here. Okay, so black holes are weird objects, and then you might wonder whether all these things really exist. So this is a picture, a time-lapse picture from the center of our own galaxy. So this cross marks the center of our galaxy, and then you have all these stars which you can see around it, and these stars are just seen to be orbiting around here. This is the years running around here, so it's like on the scale of a year, this will do this. And you can see a very funny thing, the stars come close to this place, and then they just turn around. Okay. But there's nothing here. The star is just meant to mark the place. There's no light coming from there. And so this, we believe, is the black hole at the center of our galaxy. You see, you guys come and turned on so sharply. It's a black hole of about 1 million solar masses. And you can see that these guys are just zipping around, but no light is coming from there. From last year onwards, we have a picture actually of a black hole taken by the Event Horizon Telescope of the galaxy M87. Okay, so you can now see there is sort of a hole there. It's a little puzzling as to what this picture shows. People don't quite know what this picture is showing. They just get this picture, but where is this light actually coming from? That's not very clear. It could come from the accretion disk around the black hole, or from the jets around which come perpendicular to the accretion disk, but most likely they come from the base of the jet and a bit of the disk. Somehow when light comes out from a black hole, it's not very easy to see because it bends so much. It's not easy to see where it's coming from. So you just see the outline of where the region from which you can catch a black hole, but you can't actually see what exactly you're imaging. But in any case, the fact that you see a hole in here tells you that what you're imaging at least has a black hole in the center. Okay, so these weird things like black holes seem to exist. What we're going to argue about today is what's inside the black hole. Is this a standard general relativity picture where the black hole is empty, just a tear in space-time, you go in and then you can't come out, or is there something else in there? Okay, so now let's come to the work of Hawking. And Hawking discovered that black holes have radiation. And to understand his point, we can first go to an effect which is called the Schwinger effect, which is just there in electromagnetism. So we leave gravity for the moment and talk about something called the Schwinger effect. And the effect goes in the following way. Just in the vacuum, you have vacuum fluctuations. So even in this room right now, you have electron-positron pairs that come out of the vacuum and go back in. That was just a cartoon. You saw these particles fluctuating out and then fluctuating back in. Okay. So now let's see if we can do the following. Now just take a battery here and connect it to a metal plate on this side and a metal plate on this side. So this plate gets positively charged and this plate gets negatively charged, but I have not closed the circuit here. So you might think that no current flows here at all. Now that's not exactly true. Classically that is true, but quantum mechanically, actually there is a very small current which is moving through the vacuum. And as you make these charges bigger and bigger, the current actually becomes more and more. And in fact, if you could make these charges really very big, then actually you could get a sizable current to come out in this situation. Well, where does the current come from? If this is an absolute, just a vacuum, how can it have any conductivity? Well, let's see. So we can have a vacuum fluctuation, electron-positron pair can pop out of the vacuum, and if I did nothing else, if I didn't have any of these plates around, of course in a short time it would annihilate back again and disappear. We just had that happening before we put these plates in. But now that these plates are here, what's going to happen is that the electron gets pulled towards the positive plate and the positron gets pulled towards the negative plate. Okay, so in fact there is a current flowing, because if the electron gets pulled here, then it can of course move through here. You know, electrons are attracted by the positive plate of the battery, and then the electron gets pushed out of here, and then it meets the positron over here, and you can see the loop is closed. So in fact the vacuum keeps producing the electron-positron pairs, and normally they just go back in, but if the electric field in the region, then the electrons go here and the positrons go here, and that's a current. Electrons flowing this way is the same as negative charge going this way, same as positive charge going that way, so there's net current that way, and that's the current which you actually get in here. The stronger you make the electric field, the more current you can actually pull out of the vacuum, and that's the Schwinger effect. Yes?
I'm sorry, how much is the maximum distance those two plates can have, so this effect happens?
Okay, so it doesn't matter how much power, how much voltage you take here and how far apart you put the plates, there will always be some current. It's never zero, because there's always some quantum fluctuation which, so normally they'll just recombine, but if there's some force, there's some probability the guys will separate. But the actual probability, the particle creation is very low, it's exponentially suppressed, unless you have as much electric field as would do the following. So that was my cartoon, so give me a second. Let me see if I can draw an answer to what you're asking on the board. It's a precise question, does have a precise answer. So if I produce a pair of particles, Okay? This one has an energy mc square, and this one has an energy mc square. Okay? So I need an energy 2 mc square, and that has to come from somewhere. Now this particle will go in the electric field and fall here, and this particle will go in the electric field and fall here. If the electric field is E, then you know that if a particle of charge Q moves a distance d in the electric field E, then it gets an energy equal to Q times E times d. Okay, that's just a definition of electric field. Electric field is the gradient of the potential, so the energy you get is electric field times the charge and how much you move in it. And now this guy moves a distance d, and this guy moves a distance d, so I get QED, and this guy gives an energy QED. The negative charge comes here, positive charge goes here, they both gain energy because they go in the respective directions. So the energy I gain by falling in the field is 2Q E times d. So the energy I get by separating them should be equal to the energy I paid in creating them. Then energy is balanced and the process can just keep happening. Then there's no separation. So if I put 2 mc square equal to 2q electric field times d, the 2 cancels, and you find that I need the distance d between them to be mc square over the charge times E. If this is the electron, you can replace this by E, the electron charge. If your plates have that much separation, you will get a production of pairs. So that's the case. If we have that much E, as the electric field drops below that value, the rate becomes exponentially suppressed. But when the electric field is that strong that the distance between the plates and electric field satisfies this condition, then the quantum fluctuation of mc square can become a real fluctuation because it can gain that energy out of the charges.
So later for the information paradox, you can replace the electric field by the gravitation.
That's what we are going to do. So that's why we talked about the Schwinger effect, because as I was going to show you right in the next slide, so those were my vacuum fluctuations, that's the Schwinger effect here. But now the point is, let's see if we can do, so these guys keep coming out of the vacuum, and now let's come back to the black hole. So here's a black hole, here's the center of the black hole, but now in the black hole we don't have opposite charges. Like here there was the electron went one way and the positron went the other way, so I could tear them apart. But in gravity everything falls the same way because everything has positive mass. So how can we tear them apart? Well, we can't actually tear them in opposite directions, but if you look at a black hole, the gravitational field will be strong close to the hole and weaker far away. So this side is stronger attraction, this side is weaker attraction. So as long as there's a difference, that's okay, right? If a pair comes out, there's more pull here than here, then they get separated. So, but in fact, that's exactly what happens. So what's going to happen is, if a particle pair is created near the horizon, then in fact, they end up getting separated. One guy flows off to infinity and one guy just falls in. There are much more technical ways of doing it, of course, and that we have been talking about in the technical lectures, but the actual mathematics of this is exactly the same as that in the Schwinger effect. Yes?
Where does this initial energy come? Due to the quantum fluctuations they are generated, but where does this initial energy?
Right, so that is actually from the basic source of fluctuations in any quantum theory. So for example, if you take a harmonic oscillator which is just made from a pendulum, which is like hanging from the roof like this, and suppose I give it no energy, you will say it has no fluctuations. But of course in quantum mechanics we know that's not true. It actually has fluctuations like this, because if I plot x, there's actually a wave function which has energy a half h bar omega. Okay. So it's actually those wave functions, it's actually those fluctuations, and it's actually very close to the harmonic oscillator problem, because when you do quantum field theory, instead of the position of the oscillator, you look at, let's say, the strength of the electric field. In the vacuum you would think electric E is equal to 0, but that's a classical statement. Quantum mechanically E cannot be exactly 0, it will be fluctuating, and if you plot the amplitude as a function of E, the wave function will not be at E equal to 0, but it will have a bit of a spread. And the spread basically means there's some electric fields around, and those are the fluctuations of the photons. So if you want to know photon fluctuations, they are just the fluctuations of the electric field. And if you take the field of the electrons and positons, they have their own fluctuations. So that's where the pairs are coming from. Okay, so now these guys keep getting created and you keep making these pairs, and then this is a process called Hawking radiation, which Hawking found in 1974, and the math of this is completely well understood because it's something as simple as Schwinger effect, you can just solve everything, and this is basically the same mathematics. Okay, so what's the puzzle with this, the paradox? And the serious problem that we run into is the following. Again, here's my pair of particles, it gets created and these guys run off like this. But when some energy comes out, the remaining black hole has to become smaller because energy is conserved, and so the black hole has lost some energy. And so when the next pair comes out, the black hole is going to get even smaller. See, it became even smaller. And if I keep doing this, in the end the hole is going to disappear and I'm going to have all this radiation left. let's make a crude understanding of what the problem is when this happens. And the problem is the following way. You can take a large bunch of one kind of object, let's say apples, and then if there's enough of them, they will collapse and make a black hole. Let's also take a large bunch of something else. This is a bunch of oranges, but the total mass of oranges is the same as the total mass of apples. So these guys will also collapse and they will also make a black hole. So let's just see if our pictures will do that. They collapsed and they both made a black hole. Now these black holes actually have the same mass because I took the same mass of apples and the same mass of oranges. So in fact the black holes are completely identical. If there's any difference between them, it's all in the center because my apples went here and my oranges went here. But certainly there's no difference in here because here all I feel is a gravitational field, and that comes from the metric of the black hole, and that depends only on the mass of the black hole, so that's the same. Now these particle pairs which are being produced, now they are being produced because of the gravitational field. Just like the electric field in the Schwinger effect was tearing the particles apart, we didn't care who was creating the electric field. It could be created by electrons on the plates, it could be created by muons on the plates. We only care about the electric field because that is pulling the vacuum fluctuations apart. Similarly, in the Hawking effect, we only care about the gravitational field because that is pulling the vacuum fluctuations apart. So in fact, the vacuum fluctuation will be identical, and so and also the pull on them is identical. So in fact, there's no information in what is being created here. These objects out here have no information on whether we had apples or oranges in the two different black holes. And so in the end, when the black hole is gone and only the radiation is left, the problem is this final state of the process which has radiation is going to be the same. It has no information of the initial state, which was the apples or the oranges. So this is what is called information loss. It's a crude way of understanding the information problem. We started with two different states, that they both made black holes, and then they both created particle pairs. In the end, I have the radiation, so energy is conserved, but my information is lost because my information about apples versus oranges is gone. Somebody had a hand up. Yes?
So the escape velocity near the event horizon is near to the speed of light, right?
Yes, yes.
So in order to conserve the momentum, the inside particle should also have the speed of light. So therefore, it has a high amount of momentum. So how does this lead to the fact that it is reducing the total energy?
Okay. So let me see how I want to answer that. The ultimate answer to this, of course, is that we are not really dealing with particles. They are actually waves. And so just thinking all the time in classical things may not actually help me. But let me also try to see if I can write down what you are asking in pictures. So momentum conservation is a funny thing if I actually try to see how the particles are moving. Actually, it turns out that if this is how I draw the horizon, so the horizon of a black hole is actually a 45-degree line because a light ray moving along the horizon doesn't manage to escape. So that's how the light ray goes in general relativity. A particle just outside, a light ray just outside manages to go this way, and a light ray just inside manages to go that way. Okay? So in fact, it's not like they're being kicked apart very hard like that. What is happening is they are both actually trying to go the same way. Neither of them is actually going in. The outside particle is here and the inside particle is here. Of course, I'm drawing pictures here, so they seem to be going like this. But if I draw the space-time diagram, this is space and this is time in some rough way of talking, then in fact, they are actually both going the same way. So when you actually see particle pairs being produced, this is also a particle trying to go out, but it's just inside the horizon, so it doesn't manage to make it out. It basically falls in because something inside the horizon gets sucked in, even if it is trying to go out. This guy was trying to go out and just manages to escape after a long time. So it's not like they were repelling each other very hard. They were both trying to move out, but because of the structure of light cones, these guys can escape, and here the light cones are such. The light cones sort of look like this, right? So anything which is inside here the light cone is sort of tilted like this. So you just keep going in. Even if you're trying to go out, you go in. Of course, you are thinking of a particle which is going in very hard, and that would be something like this, but that's not the member of the particle pair which is involved in Hawking radiation.
Yes, but this is for the massive particles.
Yes.
How about massive?
Well, the same. The massive particles also, when they are coming out at this point, they have a very high energy, and you can approximate them as massless. They're going to move just at the edge of this light cone, as close to the edge as possible, very close to the edge. They're not trying to go in, they're still trying to go out. And just because they are massive, they'll take a little more difficulty to come out, so massive particles radiate with more difficulty, but it's not like they are being shot in. It's not like they are shooting each other like. Well, kinetic energy is not actually a very good concept in general relativity, because it depends on which frame you're looking at. In a local frame, when you go there, nothing is moving. But let's talk about it in more detail later on. So that's like a GR question. So, but it's an important one, so we should talk about it, yes.
Is there really this kind of problem? I mean, do we know any black holes experimentally getting lost completely?
By Hawking radiation? No, we don't actually know that, and that's because the black holes we know have masses of like 1 solar mass, or the galactic ones have mass of 10 to the 8 solar masses. So the evaporation time for a 1 solar mass black hole is 10 to the power 120 years. But the age of the universe is only 10 to the 11 years. So a solar mass black hole, you will never see it evaporating. But if we had a black hole which is much smaller, if we had a black hole of mass 10 to the power 16 grams, it would evaporate in the age of the universe, 10 to the 11 years. So in fact, people have looked in the sky for signals of evaporation of primordial black holes whose size is 10 to the 16 grams. The point is, small black holes are not easy to make today because you have to squeeze the stuff into a small time. So only when the universe was very dense, there might have been some process which produced small black holes. Today, the only way we know how to produce black holes is by having a star having an endpoint like a supernova explosion, and the back reaction of that just blows it in and makes you a black hole. So some big astrophysical process can make black holes, but then you get solar mass black holes. You don't actually end up getting tiny black holes. As solar mass black holes radiate too slowly because the wavelength of Hawking radiation is set by the radius of the black hole. Solar mass black hole is 3 kilometers, so radiation coming from that is 3 kilometers. The temperature of a 3 kilometer wavelength is very low. You have no hope of seeing that in the sky. Okay, so you can see how we have lost information. The radiation is the same in both cases, and you can see where the problem came from. The problem came because the radiation came from the horizon. It got pulled out of the vacuum. That's not how normal bodies radiate. If you burn a piece of coal, the radiation comes from the atoms in the coal. So if you had an atom here on the surface, the photon will go here. If you had an atom here, the photon would go there. So different pieces of coal will give you different radiations. But if you're going to pull the thing out of the vacuum and the gravity is the same in both cases, you will not have any information. So it's a very basic problem. You can just see the problem right here in pictures. And so then Hawking said quantum mechanics is violated because in quantum mechanics, any initial state evolves this way to a final state, and so you can turn it around. You can get the initial state from the final because you can get the final from the initial. So everything is reversible in quantum mechanics, but now this time it's not reversible. We have taken two different initial states, apples and oranges, and we get the same final state, and that doesn't make any sense. That cannot be fitted into quantum mechanics, and so you get the black hole information paradox. Well, then string theorists have to worry about this because string theorists are trying to make a quantum theory of gravity. In the beginning, they were quite happy because they're not worrying about it too much. You can see a happy string theorist there. It turned out they were actually thinking it's not a serious problem for the following reason. They were thinking that if you have made black holes of one kind, it does make something slightly different in the center here as compared to making it from oranges. That we agree. There's some small difference here. And then they thought because of small difference here, they might create a small change in the way the pairs are being produced. So I've drawn the small change schematically by saying, look, here they're going this way and here you're going that way. There could be a small change like this, and then these little changes might actually hold the information about whether you have apples or whether you have oranges. Even this is not easy to get because when you actually look at the light cone diagram, if this guy has to affect this, the effect is outside the light cone. So it has to be some information which is traveling outside the light cone that is faster than the speed of light, and we don't know any such effects in quantum gravity, or in at least normal quantum field theory right now. So even if this effect was to be there, you'd have to use something which is acausal, going out of the light cone. But, well, we don't know that much about quantum gravity, you might say, so it's possible. So I've drawn some cartoon picture of these small corrections, and then you might think that these corrections are very small, but because there are so many particle pairs which I'm going to emit, somehow the subtle encoding of information, exactly what the particles are doing, might actually end up recovering all the information. And if that was true, then the Hawking puzzle was a non-puzzle, and we could actually say there is no information puzzle. And so this was the bet that Hawking actually surrendered in 2005. So this is Hawking, this is Kip Thorne, and they had taken a bet with this guy, John Preskill. Preskill was saying that the information problem will be solved in the sense the information will come out, but I don't know how. And these guys were saying, no, information is clearly lost. We are general relativity people. We can see that no information can come out of the black hole. And so in 2005, Hawking said, look, it's true, I did not do any subleading corrections, so let me surrender the bet. And the bet was a bunch of sports encyclopedias, and he mailed them all to John Preskill. Okay. And then Kip Thorne refused to pay up, because that's the cross here, he refused to pay, and he said, look, you haven't actually shown me how the small corrections can actually encode all the information. I need to see some calculation. Just saying there can be so many small corrections doesn't convince me, and so it's just the bet was never completely settled. Okay. But it turns out, so you can ask who is right, but it turns out in this case, Hawking surrendered for a wrong reason. In the end, Pascal is still right because we think in string theory information is not lost, but the reason for which Hawking surrendered is not correct, because we can actually prove that if the correction at each stage are of order epsilon, then the fraction of information that you can recover is at most 2 epsilon. So in fact, if you have small corrections, even though you're going to emit many particles, you cannot actually recover any sizable amount of information. To prove this, you require some statements from quantum information theory, like the strong subadditivity of quantum entanglement entropy. But then, in any case, the final answer is that you just cannot solve the problem by using any delicate coding of information in the emitted radiation. Okay, so if this also doesn't work, then what is the solution? So let's try to see what we can get out of string theory. So string theory looks like a weird theory, and most people who are not actually working in string theory don't seem to like it. And they don't like it because all the features in it which they see are like so different from what you actually see in normal Einstein gravity, or which you observe in the sky around you. But it will turn out that it's exactly these particular features that help us to solve the information puzzle. So let's go through some of these features. First of all, string theory lives in 10 dimensions. So there's 9 space and 1 time dimension. So if you're trying to make a black hole in our usual 4 dimensions, then the other 6 dimensions will have to be compact circles. We already talked about the fact you can have extra dimensions. As long as they are small enough, they can be, they will not see them. So 6 out of those 10 dimensions must be little circles. So people start saying, look, that looks weird. But it turns out if we don't have these extra 6 circles, we can't solve the puzzle. So it's very important that string theory actually lives in 10 dimensions and doesn't work in 4 dimensions. Yes?
Why 10? String theory can choose its dimensionality? Or?
No, it's completely fixed to be 10. And the way you get it mathematically in the beginning looks completely strange. It turns out that if you actually try to take a string and look at its vibrations, and you try to see, the string theory should at least contain a graviton in it, which should be a massless particle. Okay? If you actually take a string loop, it has some vacuum fluctuations of its own, right? If you have vacuum fluctuations of something, of a string, it just behaves like a scalar field living on a circle. Now, you might have heard this word Casimir energy. How many of you people have heard the word Casimir energy? Okay, good. So if you have energy, if you have a scalar field living in a compact space between 2 plates, of which is the same thing as on a little circle, it actually has a Casimir energy which is negative. So the string by itself, even though you don't even put any vibrations on it, the vacuum state of that string actually has a negative energy. Okay, so that's weird. We wanted to get a massless graviton, but we've got a negative energy, and we don't know what to do with that. You shouldn't have any negative energy stuff in your theory. But then if you add some vibration energy to it, then the energy can be brought up. And then you can bring it up to 0. But vibration has a definite amount of energy, because if you have a string of length L, if you put a vibration on it, it will have energy 1 over L, or 2 over L, and so on. So as you increase the number of dimensions that the string lives in, the more degrees of vibrations it has, and each kind of vibration it has acts like one scalar field living on the string, and so you get that much negative Casimir energy. If you have exactly this many dimensions, 10, then the negative Casimir energy is actually exactly enough to be cancelled by 1 unit of vibration. And that's the beautiful way it works out. If you take, let's say, some 7 dimensions, you'll have some amount of negative energy. You add 1 vibration, it will go positive. You'll never actually get 0. And so you can never actually make a massless graviton out of it. And it's actually really beautiful that initially the energy actually goes negative for just a string loop with no vibrations, because when you add 1 excitation, you got to choose which way the guy is vibrating. You have to choose an index. You have to put 1 vibration going clockwise, 1 going anti-clockwise for technical reasons. Each one carries an index, so the massless particle carries 2 indices, and that is G mu, the metric. It automatically comes out with the correct indices. So the whole thing actually fits very beautifully, but because you need the Casimir energy to be negative exactly minus 1 unit, so that you can actually cancel it by 1 unit of adding energy, that's why you actually need to be exactly 10. Okay, so you have 6 extra dimensions, and there'll be these circles, and we are not supposed to see them because we see only 4. So that's one weird feature of this theory. Then secondly, instead of point particles, we seem to have extended objects like strings and branes and all. We have all these sheets instead of point-like particles, and people haven't seen that in the lab around you. So you say, that's weird. You're telling me there's a string, and then you're telling me it's so small, like Planck size, that looks like a particle. Why should I believe any of that? But we see the fact that the objects are extended is crucial to solving the black hole puzzle. And you can see how that's going to work out, because if you just have some particles, point-like particles, and you put more energy in it, like a black hole has a lot of energy, mc square, right? If you take a lot of energy in point particles, what can point particles do with extra energy? They can just run around faster, Okay? But if you have something which can stretch like a rubber band and you put a lot of energy in it, then what can happen? Of course the guy can move faster, that is still there, but also it can stretch. Okay? So as it stretches, it can just become bigger, and we'll see that that's a new kind of effect which is going to get us to a whole new solution in string theory, which we would not have found in normal particle physics. The third thing is the coupling constant, which makes particles split and join, denoted by the symbol G, is actually variable. It's actually a field. It's a scalar field coming from the dilettone, so you can think of it as being small or large. There's a scalar field. I can send a pulse of scalar field in this room, which makes it, let's say, go from a small value and rise to a big value, and then maybe the pulse goes down again. So when that wave of scalar field is coming through the room, the coupling constant could be small here. For a while it becomes big, and then it becomes small again. Okay, because it's the value of the scalar field which is the coupling. Okay, that sounds weird, because normally coupling constant thing like electrostatics and so on, just alpha 1 by 137, it's all fixed. But here the coupling is variable. It'll turn out this is a very useful technical tool for understanding black holes in string theory. So all these look like weird features, but we are going to use them. There were already some hints in the early days that string theory might be a useful object in understanding black holes. If you just take a string which is vibrating, okay, you put some energy to a string and the string is vibrating, it starts emitting some energy, just like a guitar string. If you pluck it, it emits sound waves. So vibrating string can emit gravitons, and you can compute the rate of radiation, and then you can try to see if I put this much energy in the string, and for that much energy, if you make a black hole with the same energy, and here you compute Hawking radiation, you find the radiation rates are actually the same. So if you take energy E and you see what's the rate of radiation from energy E, you do it with a string or do it with black holes, you get similar radiation behavior. Okay, so that's interesting. It already shows you that the string seems to know a little bit about what black holes are doing, but doesn't really solve our puzzle, because our puzzle was that if you have two different objects which make a black hole, the information is not actually encoded. So even though the rates are the same, it's the fact that the stuff is coming out of the vacuum, the radiation is coming out of the vacuum, that's the puzzle. So like in this picture, here it's coming out of a string. There is no, if the string is vibrating this way, the gravitons come out this way. If the string is vibrating this way, they'll come out here. So that's like a normal body. What comes out depends on what's in there. But if they come out like this, the information is not there. So even though the rates are agreeing, we haven't really solved our actual puzzle. Okay, but now let's see what we can do. If we make the gravitational coupling weak, then we just have ordinary strings. They behave like rubber bands and we know everything about them, but certainly they are not black holes. They're just, when you don't have any gravitational coupling, when you have no coupling, you don't have any gravitational coupling either, you don't make a black hole, just have free strings. They're rubber bands, you can solve everything with them, and you can play around with them, and different shapes emit differently. We've already seen that. Okay? So now, how do we actually change the behavior at the horizon? If you try to say, I'll have some stringy physics at the horizon, at first it didn't seem to make any sense, because if a particle falls in, a little string loop will also fall in. So if your particle physics changes to string theory, it at first seems that nothing can happen. String the little loops, they'll also go in. How can you change the physics at the horizon? Just by having string theory. So now let's come to see what we actually found when playing with black holes a little more seriously using the entire theory of strings. So again, we started weak coupling. We take some strings and branes and we join them up together to make a bound state. And here's a bound state. The green ones represent branes, the red lines represent strings, and you make a bound state of these objects. Now it's a little difficult to talk about bound states in any theory, so it requires some technical work, but in principle it's a very well-defined question. If I gave you 1,000,000 strings and 1,000,000 branes, you join them together, you'll make a bound state. And now you have a good technical question you can ask: how big will be the bound state? Now that depends on the theory. So if you take, for example, bosons, which can do Bose condensation, and you make a BEC out of them, if the size of one boson wave function was this much, you can put 1,000,000 bosons and the size will still be this much, because they can always go on top of each other. Okay, so bosons so the number of bosons can keep increasing, the size of the bound state will look exactly the same. If you take, let's say, nucleons to make a nucleus of an atom, then you know that nucleons do hard sphere packing. Okay, they don't go into each other. So the size of the bound state grows like the atomic number to the power 1/3. Okay, that's just hard sphere packing. So how the size of a bound state grows depends on the theory, and that's the question we need to ask. So at first people thought, well, the natural scale in the theory is Planck length, 10 to the minus 33 centimeters. So it doesn't matter how many guys we put, we expect the guy to be Planck length in size, and so it's sitting there Planck length in size. What we used to draw as a dot, maybe it's smeared around to Planck length, but that doesn't really affect the physics because the particle pairs are created here, and this stuff is 3 kilometers apart from here. How can that make a difference? But turns out that's not what actually happened. When we started making the bound states of strings and branes, then we found that the size of the bound state grows with the number of particles you put in the bound state. And here I've drawn a cartoon of that. Here are my branes, here are my strings. when we do the technical lecture on this, you will see exactly how it is expanding and how to compute this bound state. So we will learn that on Monday. But here you can see this is where the horizon radius would have been, but the entire bound state somehow never becomes smaller than the horizon size, and the horizon never forms. So you never get to a situation where you're actually pulling particles out of the vacuum. Instead, this bound state just radiates from its surface like any piece of coal, and now different states are going to radiate differently. All the information comes out, and there's certainly no information loss here. So really, if this is true, and all black holes are going to do this, and from all the evidence we have right now in string theory, it seems this is the answer for anything you can try to do in string theory, that somehow the entire interior structure of the black hole has completely changed. The matter doesn't all disappear into the center, it just spreads around and makes just like a planet, if you like, and then of course there's not going to be any information loss. So in one sense, we've found a very simple and, if you like, disappointing answer to the puzzle. There are in some sense no black holes. They behave like black holes. They have all the properties of black holes, like the size and the mass, and in fact we'll see even the entropy, but they certainly don't have a horizon into which you can go in and make then negative energy particles. On the other hand, we've actually opened a whole new Pandora's box of physics, some very interesting physics, because you really have to ask, how did the Planck length physics which you expected, how did it become so big to reach out to 3 kilometers? So normally you thought quantum gravity is confined to the Planck length, because if you start with c, h bar and g, and you try to make something of the units of length, you only get L Planck, which is 10 to the minus 33 centimeters. So that's why people thought all quantum gravity stays at the Planck length. But there was a flaw in that argument. If you scatter 2 particles, it's true that quantum gravity effects only start when the wavelengths become Planck length. But on the other hand, if you're going to put lots of particles in the game, like to make a big black hole, you have to put 10 to the 50 particles in there. Now you have to ask what's the size of a bound state of 10 to the 50 particles. Dimensional analysis just gives you LP, Planck length, but if you put n particles in there, you have to ask if the bound state will be size LP or n times LP, or maybe n squared times LP. That depends on the theory. And what we are actually going to find is the size of the bound state actually scales with the power of n times the Planck length, and that's why it's completely okay in dimensional units. But the bigger the black hole you try to make by putting more energy, the bigger the bound state becomes, and in the end you can never actually make a horizon. So that's the story that we are actually finding from string theory. And so now you can see this solve the black hole puzzle. And so now the real question is, why didn't everything just get sucked into the center? Why doesn't everything just fall in? And as we started making more of these fuzzballs, the digital structure of the fuzzball became slowly clearer. And let's go back and see how we actually make these states in string theory. So here is our compact dimension. This is the dimensions we see, and this is one of the compact circles. We said we're going to use them, so let's try to use them. Okay. So normally this was a cartoon picture of the black hole. This was the inside, this was the outside. This is a 3-dimensional picture, but let's just draw one dimension, maybe this one. That's easier for me. So I just draw that one dimension. The center is over here, and the horizon is like here and here. So the other dimensions are there, but I'm just keeping one axis out of all of them. Okay, just for purpose. And so this region from here to here is the inside, and this is the outside. Okay. Now if there was an extra dimension, like in string theory, there was an extra circle like this, then this one dimension would actually be like a drinking straw. Okay, it's like a straw, and I would live there. But if I can't see these small circles, then of course I live on, it looks like a line to me, but really I have a little tube. Okay, of course, extra dimensions have been around for a long time, right from the work of Kaluza around 1918 to 1920, and at that time itself people knew there could be extra small circles. People were thinking about those, but it didn't seem to change any physics, because there's a small circle of Planck length everywhere in space-time. Everywhere there's a small circle in this room, then in fact it will be inside the black hole also. There's a small circle here, 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 and the mass will be here, and the horizon would be here. How does it make a difference? Here you would get negative particles, energy particles, you get positive energy particles. Nothing seems to make a difference. But in fact, we'll see there is something else you can do with the extra dimension, which is rather interesting. Take your drinking straw and take this middle region of the straw, cut it out and throw it away. It's not going to be part of my space-time. Then I have 2 holes left open here, and I cannot have a hole in my drinking straw. If I'm living on this space-time, if I come here, I can't just fall into nothing. But what I'm going to do is I'm going to close the ends of the straw like this. You can just close it smoothly like the ends of a cigar. Now I have a space-time which is completely well-defined. If an ant is crawling over here, it will come here and go back. If it's crawling over here, it will curve here and go back. Okay, so it's a different topology which I can get, which I can do, which is not like the old topology, but it's something else I can do if I have an extra compact dimension. I can just remove the interior. Why is this like a black hole? We'll actually find that every time we try to make a black hole in string theory, instead of actually becoming something like this, it ends up becoming this. And that's very funny, because now you can start asking some questions. What happened to all the mass m which supplied all the energy in this geometry? Well, this area is curved, and curvature basically costs energy, and all the energy is actually held by this curvature. Okay? But what happened to all the inside region of the black hole? Where it's completely gone. There is no inside. And so where can you actually put the particle to get negative energy? There is no such place, because the entire interior of the horizon actually vanished. So when we actually tried to make bound states in string theory, we took many strings and branes together, and we increased the coupling to the point where it would have made a black hole. This is what we would naively have expected, but this is what, when the whole thing back reacted on geometry and created something, this is what it ends up creating. And now you can see there's actually no information paradox, because there's no place to actually have a negative energy particle. That was a one-dimensional cartoon picture, but now you can think of this as a more three-dimensional picture. So how would the picture look? Suppose I want to have a black hole in the middle of this room. So what I do is I take a whole region from the middle, or the horizon size, I cut it out, and I throw it away. It's not part of space-time. Then you will think, if I keep coming up to there, what happens when I reach the boundary of the region I threw away? Will I fall into nowhere? That's not supposed to happen. If I only had 3 + 1 dimension, that would happen. But now I have an extra compact circle everywhere. So as I come to the edge of this hole which I cut out, the compact circle pinches off like a cigar. It closes like this. I come from here, it closes like this. So in every direction I'm coming, it just closes off. And if I do that, my space-time is a completely well-defined manifold. I go like this, I just turn around and come like this. I come here, I come back like this. It's a completely smooth space-time, but there's no inside of the black hole, and there's actually no place to actually get any negative energy particles. And so every time we actually try to make a bound state, now people have been doing this for over 15 years, we always find this, and we never find the traditional black hole. Okay, so that really solves the problem, but actually in a sense it opens more questions than it answers at this moment, because really, as we said, the question is, why does semi-classical physics get violated so badly? So let's go back and ask the question, how will fuzzballs form? So it seems that this solves a logical problem. If the black holes are like this, radiate from the surface, they're like pieces of core and there's no puzzle. But if you take a star and you let it collapse and you just put all the equation general relativity in a computer, it just goes in and makes a black hole with everything being low energy density, low curvatures. It looks like general relativity should be valid. So we really got to answer the question, why did general relativity break down and put us in this bizarre world of string theory where dimensions are pinching, space-time is changing, and the whole black hole structures become different? How did quantum gravity become so important at astrophysical scales? That's the real lesson we are probing. How did quantum gravity just crawl out of the Planck length and into something of the size of a black hole? There must be some magic, because a collapsing star seems to be all like a classical guy. Once it becomes a Planck scale object, maybe then quantum gravity may set up, but we really want to change the physics over here. And why did that happen? So for that we have to go back to the work of Jacob Bekenstein from 1972, who actually said, based on thermodynamic arguments, that a black hole should have a large entropy. If this is the surface area of the black hole horizon A, you divide by G, you put some C's and H bars in the appropriate place, which is basically equal to taking the area of the horizon, dividing it into squares of length, Planck length squared each. You take the horizon area, you see how many Planck length cells fit into it, and that's the entropy. Now entropy is the log of the number of states. So if you actually want the number of states of a black hole based on this hypothesis, then you have e to the power the area upon Planck length squared number of states, and a solar mass black hole then would have 10 to the power 144 states. Okay, so these thermodynamic arguments told Bekenstein that a black hole is an object with an enormous amount of entropy, far larger than the states of normal matter like a gas with the same energy. So black hole really is something very interesting. It has a very large number of internal states. We're actually going to see that that effect is going to be very important in showing us why semi-classical physics is violated in the collapse of a star. Okay. So if you just take a normal physics, you don't get this much entropy, but Bekenstein's ideas told us that black holes have an enormous entropy. Can I just check how many people have heard of the entropy of a black hole being area upon 4G? How many guys have heard that statement before? Okay, some people, but not everybody. Okay, well let me assume for the moment that this is true. Black holes have an enormous amount of entropy, which means a large number of states. So now consider the probability that a star is collapsing. Normally it would just pass through its horizon radius and go all the way to the center following classical physics. But there's always some probability that the collapsing star actually undergoes a quantum tunneling process and becomes a fuzzball. Is that true? Quantum tunneling can take anything to anything. The probability might be very small, but certainly anything can go to anything by quantum tunneling. So for example, if a person is trying to run into a wall, normally you just hit yourself on the wall, but there's a small probability that you'll tunnel through it and come out on the other side. Now why don't you take that seriously and try to get through walls by running into them? The point is the probability is very small because the objects are macroscopic, the tunneling probabilities become small. But of course, if you are at the microscopic level, you can certainly have alpha particle tunneling out of a nucleus, and that's how you get radioactivity. Somebody had a hand.
Can we compare the probabilities between that thing to an interesting shape and the child transit to a wall? So is that small probability or not?
Yes, so this is a very small probability. In fact, for the case that we are going to talk about, a star tunneling into a fuzzball, it's even smaller because typically the probability for tunneling, I'll have the expression on the next slide, it's given by a universal formula. Typically, the bigger the object is, the smaller the probability. So it's even smaller than running into a wall and hoping to get through. Okay, so yeah. So what's going to help us is actually something else. So what happens is if you have a classical action for a process, action is LDT, the normal action that you learn about in classical mechanics, then the probability of tunneling is exponential of minus the action. Okay, so if you have a bigger object, then the action for it to change from one thing to the other becomes a bigger number, and then e to the minus s becomes very tiny. So the probability for this guy to tunnel into from this collapsing shell to tunnel into one of these fuzzballs is a very small number. However, what's going to help us is that we don't really just want to tunnel into one fuzzball. There are many, many different states of the black hole. I've drawn slightly different fuzzballs here. There are going to be how many of them for a solar mass black hole? There are 10 to the power 10 to the 144 possible states to go to. And now you see the magic. In particle physics, if you're going to scatter into some final state, you sum over all the possible final states you can go to. If you scatter two particles and they can go this way or this way or this way, if you want the total cross section for scattering, total probability that something happens, you do sum over all the possible final states. So this time I have to take the probability for tunneling into one guy, but also add the probability of tunneling into this and the probability of tunneling into this. Since the probability of tunneling is roughly the same, I can have the probability of tunneling like this, but then multiply by the number of states. But what's the number of states? 10 to the power 10 to the power 144. And it turns out if you take the, so it's like it grows with the mass of the black hole, right? It depends on the mass of the black hole, how much the number of states is. And then you find something very interesting. If you take the probability of tunneling into one of them, it's very small. If you multiply that by the number of these states, which is a big number, that number is very big. When you multiply them, you get order unity. So that's the magic. So where the place where all the new physics was hiding was in the fact that the number of possible states of a black hole are very large. So when you actually compute these fuzzball states, the different ways you get the strings and brains to join each other, the number of possible bound states, it has a very high degeneracy. And when something has a very high degeneracy, physics stops being normal because there's lots of phase-space directions into which you can go, and that actually enhances all the quantum effects, and the whole black hole physics, instead of being classical, actually becomes quantum. So you can think of the physics like this. If you have a box and you have a wave function in it, there's a small probability of tunneling into, let's say, a neighboring box, or this box, or this box, or this box. But suppose you could tunnel into a lot of different boxes. Instead of just having 4 neighboring boxes, suppose I had 1 million neighboring boxes. But the probability of tunneling was 10 to the minus 6 into any one box. Will the particle really stay here? No. The probability is very small to tunnel into this box or into this box, but by the time I take into account all the boxes, the particle is going to disappear from here and become a linear combination of states in all the other boxes. So think of this as the star and these as the fuzzballs. If there are enough different directions into which you can tunnel, in the tunneling probability into any one of them is very small. The total probability of tunneling into something is order 1, and that's why the classical approximation breaks down. So before people knew there were fuzzballs, people just thought the black hole will keep doing what it does, but now the wave function can actually spread among many other things, and so the physics really needs the physics of all the fuzzballs. And so the whole black hole is actually a very quantum object. You can't really think of taking all this star and actually localizing it into its well-defined thing, because it can keep tunneling into all these different states and just becomes a linear combination of all these guys. So the black hole is very big, but because of the very large phase space of states, the classical approximation is violated. Okay, so let's summarize what we have learned, reaching the end of our time. So again, starting back with Hawking's work in 1974 and then the consequence of that in 1975, general relativity gave us black holes, and then Hawking found Hawking radiation in 1974, and 1975 he noticed that this was inconsistent because information was being lost. in string theory, what we are realizing is that quantum gravity effects are altering the entire structure of the hole. So in fact, you're not getting a smooth horizon with just a vacuum around it at all. All the matter is not rushing to the center. The matter is spreading out actually all over. And if that is the case, certainly you don't have the information paradox, but you learned a very deep lesson, which we need to take away from this to other situations, that quantum gravity doesn't always live at the Planck scale. The Planck scale is a natural thing you get in terms of units of c, h bar, and g. But if there are many particles involved, the relevant length of quantum gravity is roughly n times the Planck length. So when you're doing the macroscopic numbers of particles, you have to be careful. Quantum gravity could act on very, very long length scales, like what happened here. Okay. And so the lesson was that this is not what really happens in black holes. You get this and you radiate from the surface. And so this picture where you make a tear in the space-time, which was basically this black hole, well, this picture was actually not true. So where do we want to go with all this? If that solves the black hole puzzle for us, where should we take that? We have seen that the new effects are going to come in quantum gravity when we have a large number of particles, and so then if we try to put them together, then the scale of quantum gravity becomes n times the Planck length. Okay, so is there any other situation other than the black hole where we know a large number of particles are going to be crushed together? So of course we know there is one such place, and that's the Big Bang. So if we think of this as time, this is our universe, so you have radiation at some point, even later you have dust. If you go in the earlier time, temperature was higher. Maybe you had strings, maybe you had brains. And as you go here, temperature becomes higher and higher, and in fact the density becomes also higher and higher, and lots of particles are being crushed together. So in fact, whatever physics we were doing with assuming normal particle behavior just may not be true, because lots of particles get together, then we are seeing these long length scales of quantum gravity are now starting to operate. So what could be the lesson in here? The main lesson we want to perhaps focus on is what about the cosmological horizon. So in the sky we see a horizon around us, it's called the cosmological horizon, and in many ways that is similar to the black hole horizon. There are some similarities and there are some differences. So if quantum gravity can actually be important all the way up to the black hole horizon, you now have to ask, can quantum gravity play a role all the way up to the cosmological horizon? It's a very similar problem. It has the same skills involved. And so I think the really interesting story that we have learned from black holes should really now be applied to the Big Bang and to answer all the open questions that we have in cosmology. And there are so many mysteries associated to the universe. There are so many questions that we don't understand at all about cosmology, like the cosmological constant, why the universe is approximately flat, why is the universe so big, and in particular, does anything happen at the cosmological horizon? So all those questions are now perhaps can be answered because we have a complete new understanding of what a large bunch of particles do when they are crushed together. Okay, I'll stop here. Yes, question.
So I have two questions. First of all, we know that the number of microstates of a black hole is too much, as you said.
Yes.
But consider a star which is collapsing and becoming a black hole. So in the moment that it is reaching the Schwarzschild radius, it is still a star.
Yes.
But the number of its microstates should be large. Or does the number of microstates somehow jumps from a small number to a large number?
Okay, so that is the process of how the black hole will turn itself into fuzzballs, right? So we don't know that much about the process. We just know on the two sides the answer is known. So it will my guess would be it will start changing as it comes close to a Schwarzschild radius. It has to jump in number. Okay? But the numbers on each side for the star and for the black hole, they are very clear and well established. So for a star or any ordinary matter, the maximal entropy that you can have was computed by 't Hooft, and that is basically the area of the object, again in Planck units squared, to the power 3/4. And for the black hole, it is A over Planck length squared, like this. So there's a big difference because it just looks like a quarter power difference, but because this is a huge number, the ratio is huge. Okay. So black holes certainly have many more degrees of freedom, and we are supposed to understand that in the fact that once you crush something into a black hole, all the stringy degrees of freedom are liberated, and they have a huge amount of entropy.
So there is a strange jump from that number to another.
Yes, so a jump by itself is not so unusual, right? I mean, if you take some liquid and you boil it and you get into a gas, the entropy changes dramatically. So when you have a phase change where the basic degrees of freedom become different, the entropy actually changes. So that itself is not unusual. And so you really are having a phase transition. We really have to think of black hole formation as a phase transition where the effective degrees of freedom went from being simple atoms to becoming strings and brains. and so the entropy will jump.
Okay. So my second question is that with the fuzzballs being present, how do the objects fall inside the black hole?
So with the fuzzball, things will not actually fall inside the black hole. They cannot actually fall inside the fuzzball. But people often ask this question, what happens if you fall onto the fuzzball? Will you go in any sense? Is there any classical idea of going in? And there is an interesting story here called the story of complementarity, which people have been trying to develop. And there's been a lot of back and forth about the idea of complementarity. And the idea goes like this. So at least with the fuzzball, suppose we talk about the story in the context of fuzzball, you clearly can't go in. The whole thing is like a star, right? If you go in, it's not like empty space. But we would like to save our classical intuition if possible, because every time we have some classical physics, quantum physics modifies it, but some approximate classical intuition remains. So is there any approximate sense in which you can still imagine that we are falling into a black hole? And this is the idea that people were developing, which has taken many manifestations. Some of those ideas were wrong, but really the idea goes under the title of complementarity. If people want, I can say a few words about that. I had some slides, maybe in my extra slides, I have some slides at the end of my talk. Let me see if I have, okay, yeah, I have some slides on complementarity here, so let me talk about those. I have extra slides on something, let me just pick up something. So this is the idea of complementarity. So sometimes you can take two completely different systems. See, this is a piano, and this is a keyboard. They actually sound almost the same, right? Because they have some frequencies, and this produces some frequencies. But actually they are very different objects. But if you hear something in a room from outside, you can't tell if it's a piano or a keyboard. Okay, let's see if the same idea can be used to do the following. Suppose you have a particle, a photon falling onto a normal black hole, and here's a photon falling onto the fuzzball. It's just some way that this dynamics can actually, this dynamics which is real, can mimic this dynamics. Then you have some approximate idea of maintaining classical physics. So let's see how that might work out. So in quantum theory, every state is characterized by some energy E, and then Einstein told us that E is equal to h nu, so every physical system is really characterized by its energy levels, which is same as saying it's characterized by some frequencies. So you guys know that if you do quantum mechanics, you just have energy levels describing the system, and that completely characterize the system, which you can say is just characterized by some set of frequencies. Okay? An atom is characterized by some frequencies coming from the orbits. Now if two different systems actually have the same frequencies, they are indistinguishable. So this is what goes in string theory under the name of duality. Sometimes you can take one system in string theory, and then a completely different system in string theory, but they have the same frequencies, and they can actually then be mapped one into the other, and that's called a duality, because it's impossible to distinguish between them. Okay, let's see if there's any version of this which you can pull out, at least in some form, and use it for what we are asking. So if you take this guy and you let it fall in classical black hole, this guy goes in, and then you can describe the dynamics of this infall as a set of some frequencies, because any process in quantum mechanics is described by some frequencies. I've called it frequency nu1 black hole, nu2 black hole. This is what you would get if you did classical black hole physics. Okay. Now, if you fall on the fuzzball, you can't go in. Space-time just ends. So all you can do is you can vibrate the fuzzball. I've tried to draw the vibrating fuzzball here. But the vibration of the fuzzball is also given by some frequencies. I've called it nu1 fuzzball, nu2 fuzzball, and so on. Okay, now what happens if these frequencies which you get for the black hole dynamics are approximately the same as these frequencies? Okay, this is like the piano, this is like the keyboard. If the frequencies are approximately the same, in some sense, the dynamics can be mapped to being approximately the same, even though the two systems are not the same. You can't go inside the black hole, but in some way, they might mimic each other. Let's see if we can complete that argument. So what happens is, if you look at low energy emission, the photons emitted from the black hole have very low energy, and they are different for different fuzzballs, so that's why the information is coming out. These photons have energy of the order of the temperature of the black hole. They are very low energy. But if you throw in something of very high energy, like suppose you fall in, your energy is much more than the energy kT of the black hole. Then the whole thing undergoes some kind of harmonic oscillations, and it has certain frequencies, and those frequencies might approximate the frequencies which you get for the black hole. So this has to be an approximation, because all fuzzballs are different, all the states are different, so they all have different frequencies. They can't all be the same as the black hole frequency, but if they're approximately the same for heavy objects falling in, then these guys might mimic this fuzzball. So this is called the idea of fuzzball complementarity, because then at low energies you recover all the information, at high energies they behave similarly. We don't know if it is true, but because it is possible, it's a good idea to investigate it. Why do we think something like this might be true? It's a little like the correspondence principle in quantum mechanics. The quantum theory is not at all like classical theory. Everything is different. But as long as the action, any process is much more than h bar, we have a correspondence principle that basically classical results will be reproduced to a good approximation. So that's what we are hoping here, that if you are looking at energy as much more than the temperature of the black hole, there should be some way of reproducing the same effective dynamics from the vibrations of fuzzballs, but we don't know if that is true. Yes?
Now, to what degree does the string theory match with the experimental results?
So there is no observation which we can, which we have right now, which even gets us close to the Planck scale. So that way we would say nothing. The one thing which it has done so far is that it has allowed the theorists to build at least a consistent theory. So the two main successes of string theory are the following. First, it has no loop divergences. So before, when people tried to make a theory of quantum gravity, the loops actually all became infinite, and then you cannot make a theory. So this theory doesn't have that problem. So that was the first major success right from the late 70s. But the other really big success came when we understood the entropy of black holes. This idea of entropy being A upon 4G, which Bekenstein found on purely thermodynamic arguments. It tells you the black hole should have this many states for this much mass. And in a very important work by Strominger and Wafra in '96, they actually computed the entropy of what you get when you take this many strings and branes of this much total mass, and they got exactly A upon 4G. And that's really beautiful, because if you can actually reproduce the entropy by a microscopic counting of states, it means you're really understanding the microscopic entropy correctly. It's like you already knew the entropy of a gas in a box by thermodynamic games, by playing with the gas, by just, the thermodynamics of the 1700s. But then you actually had Boltzmann's theory of actually going and doing all the atoms, and you compute the entropy by doing the microscopic theory of atoms, and you got the correct answer. Okay? So then you would really know that the whole thing is really made of atoms, because you have the correct microscopic theory. So the fact that you've actually got the entropy correct, the A upon 4G, and for that you actually need to get everything correct. If you make a mistake in the tension of the string by a factor of 2, the entropy will also not work out. So if you actually had a wrong number for which kind of objects you can have, which strings, which branes, what tensions, any mistake you make, you don't get A by 4G. So it's really beautiful that this number, which can be derived without any string theory, any quantum gravity, comes out exactly in string theory. I think it completely validates the fact that as we get to the energies of a black hole, much above the Planck scale, whatever theory of quantum gravity we find will have to reduce to that theory. It may not work in today's, we don't know how to get electrons and protons very well today from it, but at high energies, it seems to be the right way to do quantum gravity. Right? Yes?
I missed the point in your lecture where you mentioned the extra dimensions, and you said there is no notion of inside and we have a well-behaved manifold. Is it related to the fuzzball, or that's a different solution?
No, it is related to the fuzzball. So what happens is when you take these strings and branes, I just drew a picture of some strings and branes, right? So that is at weak coupling, when you just have not much gravity around, you just have strings and branes and they have some size. Then as you start increasing the coupling, it starts deforming the manifold it is sitting in because of the gravitational effects. So the manifold starts changing, and then what it does to the manifold is it actually creates this kind of new topology. So the different ways of getting all these new topologies are actually all the different states of the fuzzball. So what we actually do these days when we make the different fuzzball solutions is we want to go and see how we get all these different topologies. So that's why the extra dimensions are very crucial. Where, when you go at weak coupling, which is what Strominger and Wafra did, and you try to count all the states of the black hole to get the entropy, what happens is you take the string and you wrap it in the extra dimensions, like this, and you put some vibrations on it, and that's how you get all the states of the string. If you didn't have any extra dimensions, you have nothing to wrap the string on. If you just kept a string loop right in the middle of this room, it will just run away. Okay? So you actually, the entire entropy of the black hole comes from how you wrap the strings and how they vibrate in all the extra dimensions. And if you change the extra dimension from 6 to 5, the entropy of the black hole in 4 dimensions wouldn't come out right. It will get an extra factor of 5 over 6. So really the number of extra dimensions and the fact that they're there is absolutely crucial. And when you actually go to see in the gravity, the actual structure of the black hole, the fuzzball structure, you find what's happening is, if you just took to 3+1 gravity, you have the no-hair theorem. Every black hole looks identical. There's a horizon, you go inside, you have the singularity. But now we have hair. Every different fuzzball looks different. We have found hair. So what happened to all the no-hair theorems? And what happened was, the no-hair theorems were never taking into account the fact that the extra dimensions can actually change their topology. So what is happening is the extra dimensions are having a topology which is not a tensor product. If you had a circle which is a circle everywhere, we call it a simple direct tensor product, right? You have these dimensions and you have the circle. But if you have the circle somewhere the circle pinches off, then the topology of the extra dimension changes. And this was never actually included in the Noether theorems. And you see that's what the fuzzballs actually do. So you directly start with some strings and brains, you increase the coupling and you see what they generate. So it's not a guess or anything, just go and compute that in string theory and you see it actually makes you that. So that's what that thing was. Yeah.
So in this context of having extra dimensions, how can you define the area in your entropy formula, like the area of the black hole?
Yeah, so that now will be only approximate because these fuzzballs will typically be, it's like bigger than the horizon, right? So you might say exactly whose area am I computing. But it's interesting that we do believe that the generic fuzzball will have a size which is not too much bigger than the horizon. It's like what used to be the horizon at 2m plus a few Planck lengths. So at the leading order when we are computing A upon 4g, that extra bit doesn't really matter. It's still the same area. We mentioned the area of the typical fuzzball. Yes?
My question is not that relevant, but I want to ask anyway. What do you think about the Big Bang? Is there a really Big Bang?
Okay, so I think the answer we are finding from our initial guesswork on the Big Bang, our work on cosmology is sort of just starting. It's not like I know any answers. But it seems that what is happening there is as you go towards the Big Bang, suppose you follow things backwards, what is happening is that the space seems to fragment. So suppose you have like a whole gas of radiation now. As you go to the past, it goes into little clumps, where in each clump it behaves a little bit like one of these fuzzballs. And then as you crush it down further, it becomes into even more tinier and tinier fuzzball. So instead of getting a bang where everything is crushed to a point, what is happening is that the thing just becomes more and more tiny bits, which then don't talk very much to each other. So that's what seems to be happening. But we can talk about it in detail later on if you like. So it's a different picture of the black hole. It somehow does some of the Big Bang. It does something else. Yes.
I think I do not understand this fuzzball thing good, but is that fuzzball explains the new image with event horizon? If there is no horizon and there is no inside, how that shadow can be?
Yeah, so it's not easy to observe the difference between the fuzzball or any other model for the black hole from the observations we have. Because what the image is actually seeing, it's actually seeing not the horizon 2m, it's actually seeing the light coming from the last unstable orbit, which is at 3m. Okay, so any physics you change at 2m plus a few Planck lengths and inside, the whole inside, it actually makes no difference out there. And so if you have any object out there which is highly absorptive, all these fuzzballs are very absorptive, anything which a large entropy is typically very highly absorptive, it actually makes almost no difference to the black hole, because in the horizon if something falls in, the only thing which you care about is that it goes in, it doesn't come out. If you replace it by something which is highly absorptive, like suppose it absorbs 99.9% of everything that falls in, as far as the outside is concerned, it behaves the same. So same is true for the gravitational radiation. The gravitational waves that are coming from mergers, they actually come from even further out. They come from 6m, because anything which comes inside 6m basically spirals in and falls in. Now if it falls into a horizon and goes in, or whether it falls in and gets absorbed by the fuzzball, it makes no difference to the part which is actually leaving. So what we see from black holes is typically either from 6m in the case of gravitational waves, or from 3m in the case of the black hole image, but nothing can actually show you something very close to 2m. So that's why it's more theoretical. It solves the puzzle and so on, but I don't think it's going to be easy to see.
Is there any absolute absorption in these fuzzball things? The horizon is a one-way membrane.
No, so it's not absolute. It's not absolute. It's more like a piece of coal. If light falls on a piece of coal, it absorbs at 99%, that's why the coal looks black. So let's ask why coal absorbs light. Right? If you had like a mirror, it reflects light. But why does coal absorb light? So if a photon falls on a piece of coal, it just basically creates vibrations of all the atoms, and there are many more degrees of freedom in the atoms. There's much more entropy into putting it into the vibrations, so it doesn't want to escape back, because if it escapes back, it's one state with maybe one state there, but if it goes into the coal, it can access many states for the same energy. So that's why coal is black, it just absorbs everything. So typically if anything has a very high entropy, or which is same as saying low temperature, ds by dE is actually small. Okay. So ds by dE is large, that's equal to 1 by T, so that is T is small. In that case, typically going to be highly absorptive. So once something, because the entropy here is so big, if something falls onto the black hole, there are many more excitations it can have inside as compared to leaving. So once something comes in, it doesn't want to go back. That's how all absorptions are. Nothing special about the black hole. So because the black hole has a large entropy, its absorption is going to be 99.99%, and then it doesn't matter. So in principle, of course, everything comes out. The fuzzball is like a normal object. It will come in and ultimately it will go out. But it will go out after a long time. But that it will look black and radiant thermal radiation just like a piece of coal. But there's no information puzzle. It's not lost because it's not like I had negative energy pairs and I was getting everything going with a lot of information but no mass because the negative energy reduced the energy. None of those things are happening.